Random walks and unit roots. In the previous section, which was section 4, we looked at time series which were mean reverting. So we might not have said this explicitly, but we talked about mean reversion, we talked about the mean reversion formula, and we generally looked at data which was mean reverting. If you look at gross margin data or inflation data, generally that is mean reverting. You will never have a company that has gross margins that are constantly increasing, right? If you find one, let me know. But there are many financial time series in which changes are not mean reverting, changes follow a random pattern. That random pattern is simplistically called a random walk. In this particular section, we have two subsections. We get into a little bit of detail related to random walks, and then we talk about something called the unit root test of non-stationarity. Let's start with a formal definition of a random walk. A random walk is a time series in which the value of the series in one period is the value of the series in the previous period plus an unpredictable error term. That unpredictability of the error term is what makes this a random walk. Very often this model is used with currencies, because with a currency the value in the next period is the current period plus some random change. A lot of people try to apply technical analysis and other analysis to figure out what the exchange rate will be in the future, but sufficient studies have shown that this particular variable, currency exchange rate, follows a random walk. All right. When you show that something follows a random walk, then that would imply that your most fundamental analysis, or that would imply that fundamental analysis does not work. Right? If things are randomly going up and down based on a previous value, then clearly fundamental analysis is not of much use. Also, this notion, just as a side remark, was popularized by this very famous book called A Random Walk Down Wall Street by a Princeton professor, where he argued that even stock market movements follow a random walk. So while many might disagree, so Warren Buffett disagreed with that, but it is an interesting book that you can read after your level 2 exam. Okay, now so what is the formula that we talk about in the context of random walks? Your x value at time t is equal to the x value in the previous period plus some unpredictable random error. And some mathematical things that we also need to be aware of. The expected value of the error should be 0. The error should have some variance which is not changing, and the correlation or covariances should be 0. Okay. Just keep these at the back of your mind, and this is the equation that we will largely focus on. What is the mean reversion level with this equation? And here, if you recall, I asked you to remember the mean reversion formula. What was that mean reversion formula? What's the mean reverting level? It was B0 over 1 minus B1. What is B1 in this formula? What is B0 and what's B1? B0 is 0. What is B1? Yeah, you have nothing over here. So as you learned very early in your maths education that nothing means 1 in this context. So you have 1. If B1 is 1, what's the mean reverting level? It is infinite. It is unspecified. Okay, some people might have said 0 and they should be spanked. Right? So anything divided by 0 is unspecified, infinite, undefined, and so on. So in this particular case, we do not have a mean reverting level. If we don't have a mean reverting level, that means that the mean can keep changing. If the mean can keep changing, then is this data covariance stationary? No. So the answer to the first is infinite, the answer to the second is no. If we are not covariance stationary, can we use standard regression analysis? No. Right? So what do? We need to do something else. And that something else is called first differencing. Alright, so let's talk about this concept of first differencing, and then we will do an example which uses first differencing. Now these are not perfect pictures, but they just give you an idea. So if you have time on the x-axis and you have a given variable that seems to be randomly going up and down, okay, just looking at this data, does it look covariance stationary? No, because it looks like the mean is generally changing, it's going up. In this particular case, you can't really tell whether the variance is changing or not, but it is easy to see that the mean is changing. So what you now need to do is something called first differencing. With first differencing, you take the difference of the x values and regress that. So you define a new variable called y. Your y at time t is the first difference of the x's. So if this is your x variable, which is changing with time, you define y like this, and this is a bit of a transformation. So y at time t is defined as x at time t minus x at time t minus 1. Is this a first difference? It is. It's a first difference of the underlying variable, which is x in this case. All right. Then what you have plotted over here is the y variable. Sometimes you might just call this the y variable, or you can call this now xt minus xt minus 1. Right? This will have an expected value of 0. Right? So you notice that over here. Is that expected value changing? So even though x, or the expected value of x is changing, but if the change in x every time is random, and that change in x or the error has an expected value of 0, then the first difference of x will have an expected value of 0. Sometimes the change will be positive, sometimes the change will be negative. And going back to the fact that currency rates often seem to follow this trend, if you take the euro-dollar rate, does the euro-dollar rate stay the same? No. Some time ago it was 0.8, now it might be 1.3, but the change tomorrow is going to be random. If the rate today is 1.3, then tomorrow it might be up a little or down a little. You don't know exactly, but the difference every time is what we are looking at over here. So this is first differencing. Then what you do is you regress yt with yt minus 1. Right? So you do this transformation. Is that straightforward? I hope it is. It's just a subtraction. Then do you have a new column or a new set of data for y? Right? So you have the y data across different t's. Yt means the difference between xt and xt minus 1. So if you think in terms of Excel columns, can you have a column for yt for different time periods? You can. Then can you regress yt with previous versions of y? Isn't that a simple AR1 model for y? Is this data covariance stationary? Appears to be. So can we run regression? Yeah. Could we run regression simply with x? No, because it was not covariance stationary. Alright, so we are now going to look at example 10, which deals with the yen-dollar exchange rate. I'm skipping some data in the curriculum and just zeroing in on the most important aspects. We first run a regression where we do not do any first differencing. Okay, so we are looking at this exchange rate and we are regressing the exchange rate with previous version of the exchange rate. So we are simply regressing the x value, not doing any transformation, not doing any first differencing. And these are the coefficients. Do you see a problem here? The big issue here is that lag 1 is very close to 1. Like 0.99 is almost as close to 1 as you can get. When lag 1 is very close to 1, that means that we have a random walk. Remember the definition of the random walk that we just talked about was if you have xt is equal to something plus b1 times xt minus 1. What we are saying is that this b1 is 1, and we can say that with a lot of confidence, right? Because we have such a high t stat. What about this term? This actually has a very low t-stat. So this looks like 0 in the sense that you cannot reject the null hypothesis that the intercept is 0. But the real issue is this, that we seem to have a random walk. So just put it in your head right now, if the slope coefficient or the B1 or the lag 1 actually is 1, then that implies random walk. And random walk implies that non-stationary data, which means that the regression cannot be used. So what do? As you've just learned, you do first differencing. And obviously on the exam, you will not be doing the first differencing, you will be given the output of first differencing. And now we have this. Look at what happens to the lag. The lag now is definitely different from 1. Okay, so that is the big improvement. What about the autocorrelations? Do we need to check whether there is a correlation between error terms? In general, with time series, that's the big thing to look for, because that is the major issue that we generally have with time series data. So in general, you look at these. Do we see a problem here? So what do you immediately look at? This is the column that you look at. Right? All these are less than 2. Does that make you happy or unhappy? Assuming that this is your model, it tells you that this is a good sign. There doesn't appear to be autocorrelation between the error terms. So you have a better model. Before I move to the next slide, I just want to make a comment about the R squared, which I have not shown here. But if you look at the curriculum, there is a table 9. In the table 9 is where we do the regression without first differencing. And there the R squared is quite high. There the R squared is 0.99. And then when you do first differencing and you get your regression output, then the R squared, which is shown in table 10, is much lower. It is 0.0053. This might seem strange on the surface because with first differencing, the R squared is coming down. But as you go deeper, you'll realize that this does make sense, because when you are predicting using just the X value, not the first differencing, the best predictor of the exchange rate in the next period is the current rate. So when you do that regression, the R squared seems to be high. But when you do first differencing, then what you are using is the difference of the X's. So if you compare the difference of the exchange rate today with the difference in exchange rate tomorrow, if we are saying that's random, then obviously the change in exchange rate from one day to another cannot be used to predict the change in the exchange rate between tomorrow and day after. Right? So that's why this R squared is so low. And this also leads us to a larger point. If this analysis demonstrates that we have a unit root, and it demonstrates that the changes are completely random, then should you be spending a lot of time trying to make money on currency fluctuations? This analysis would indicate that it doesn't make sense. You will make money some days, you will lose money some days. The expected value of how much you make is 0, according to this analysis, unless you find something that really works for you. But based on academic work, currency trading will have an expected value of 0. All right, moving on, we'll now talk about the unit root test of non-stationarity. A fancy new term is introduced, but we have actually seen this before, and this is quite testable. You need to learn a few terms. If a time series comes from an AR1 model, then to be covariance stationary, the absolute value of B1 must be less than 1. This is extremely important. So B1 is our coefficient, and this has to be less than 1 for our data to be covariance stationary. which means that if B1 is greater than or equal to 1, then we have a problem, a big problem. Then we cannot use this particular model. In fact, a specific scenario happens when B1 is equal to 1. Then we say that the time series has a unit root. It is a random walk and is not covariance stationary. And again, we've seen this before, because what is a mean reverting level? It is B0 over 1 minus B1. So we see that formula again. If B1 is 1, that problem is called a unit root problem. Now, why is it called unit root? You can come up with any way of remembering this, but I would say that it's down in the denominator, so it is a root. It has a value of 1, so that's why it's called the unit root. When we have a unit root, what's the mean reverting level? Undefined. Right, so we have a problem. Another point made in this section is that all random walks with or without a drift term have unit roots. What does this mean? Not a huge point, but just a minor point. We have talked about the fact that your xt is equal to xt minus 1 plus an error term. This is a random walk without a drift, because the next value of x depends only on the previous value plus an error term. You might also have a scenario like this. Your xt is equal to 0.2 plus xt minus 1 plus an error term. Now this is a drift, that you are drifting upwards. So this introduces a drift. And the point is that all random walks, whether they do not have a drift or they have a drift, so all random walks have this unit root, which means the coefficient is 1. When you are running a model, you want to test whether there is a unit root problem or not. So your regression analysis might give you a number for this coefficient, which is 0.9. Right, now how do you figure out statistically whether you have a unit root problem or not? And the answer is that you do what's called a Dickey-Fuller test. I don't know why, but for some reason all these tests were done by 2 people. Right, you have Durbin-Watson, Bruce-Pagan, Dickey-Fuller. So for some reason it is always 2 guys who get together and come up with these tests. Unfortunately for you, you need to remember all these terms. The curriculum doesn't get into too much detail with Dickey-Fuller, but it gives some basic information which you need to know. What do we have over here? Does this look like an AR1 model? It is a very basic AR1 model. Now we want to test whether this AR1 model has a unit root problem or not. So what we do is, we do a simple transformation. With basic algebra, can you go from this equation to this equation? All we are doing is saying xt, and then you subtract the xt minus 1. So just take my word as a given. You can do some basic algebra and come up with this expression. Okay, so we have transformed equation 1 into equation 2. Now if you do the following, instead of saying b1 minus 1, just rewrite that as g1, and you'll see soon why I'm saying that, or why Dickey-Fuller said that. I'm just telling you what they've done. All right, then you regress this xt minus 1 minus, so then you regress xt minus 1, regress this against this. Can we do that? Once we have x values, you can easily come up with a column that shows this difference, and you have a column that's xt minus 1. Can you regress? Okay, you do this regression and you set a null hypothesis that g1 is equal to 0. If g1 is equal to 0, what does that say about b1? Yeah, so g1 is equal to 0. What is g1? It is simply b1 minus 1. So if g1 is 0, that means b1 is 1. If b1 is 1, so generally when we set up a null hypothesis and we do the t-test, then it is based on the coefficient being 0. That's why we do this little substitution. G1 is 0. Now, if you do the null hypothesis, and you cannot reject the null hypothesis, that means you cannot reject the fact that G1 is 0, which means you cannot reject the fact that B1 is 1, which means you cannot reject the fact that there might be a unit root problem, which means that you cannot reject the fact that our data might not be covariance stationary. Right? So I think that's what you really need to know. You don't need to get into more detail, even though what I said might sound like a fair amount of detail. But I would strongly encourage you to read example 11. At the very least, remember the fact that if we have a unit root, that's a problem, and the formal test for the unit root is the Dickey-Fuller test. Let's now look at example 12, Intel's quarterly sales data. This is something we saw before. In example 3, we considered a log linear trend model where we looked at Intel's sales. These were the actual sales, and we realized that it looks like there is exponential growth, so we used this model. Okay, now we say that we understand how AR models work. We are smarter, so let's use an AR model. The moment you get into an AR model, you realize that the data needs to be covariance stationary to use an AR model. But does this data look covariance stationary? Definitely not. So it is not covariance stationary. If the data is not covariance stationary, what do? First differencing. We do first differencing. And how does that work now? What we do is we use this expression. Two things are happening here. One is we need to do a transformation. So the data is growing exponentially. Sales generally grows exponentially. So we need to use ln. That's one point. The other point is that we need to do first differencing to deal with the fact that the data is not covariance stationary. Right? So we have this. The natural log of sales at time t minus the natural log of sales at time t minus 1. What have we done here? We have done a first difference is equal to b naught plus b1 times this. What is going on here? This is first differencing because we are looking at the difference here, t minus 1 plus b naught plus b1 times, this is t minus 1 minus sales at time t minus 2. So we are regressing the first differences. Okay, so when we run this regression, and just try to remember this expression, here is the regression output that we get. So we have the coefficients, we have standard errors and the t-stats, which both look reasonably significant. We do the autocorrelation of the residuals, and immediately we look at the t-stats. All the t-stats in terms of absolute value are less than 2. So do we have a problem? We don't have a problem. Okay, now you have a bit of a problem where I'm going to tell you the following. In the third quarter of 1999, Intel sales were this much. And I'll just tell you that the natural log is this number, so you should be able to do this on your calculators. Then in the fourth quarter of 1999, Intel sales went up to this number. I want you to predict sales for the first quarter of 2000 using the model that we just talked about. So in case you are struggling, I'll help you get started. This is the equation from the previous slide. I've just replaced sales with S. So the natural log of sales at time t minus natural log of sales at time t minus 1 is equal to b naught, which is this number, plus b1, which is this number, multiplied by the natural log of sales from t minus 1 minus the natural log of sales from t minus 2, plus we have an error term which has an expected value of 0, so I am not including it here. Now I want you to plug in these numbers and the numbers given in the question to predict the sales. And note that you'll have to do first differencing, and then you will have to do the transformation because we are dealing with the natural log over here. So here is what you do. This is what we've established from before, that the natural log of sales at time t minus natural log of sales at t minus 1 is this. From this, it can be said that the natural log of sales at time t minus 1, so the next difference, is the same. Which means, and this is actually mathematics, ln of this expression minus ln of this can be written as ln of st plus 1 divided by st. So I'm sure you've studied this at some point. That is equal to 0.0701. This is really base E. So we can then say that st plus 1 over st is equal to e to the power of 0.0701. Do we know s at time t? What is t? It is the fourth quarter of 1999 with sales this number. So the predicted value of the sales in the next period will be this expression which you do on the calculator multiplied by st, which is actually 8.212. And when you do that calculation, you should get 8808 million. So that should be your answer. Again, this is a little bit difficult and it requires some practice, but you need to know this material. So here is a question that you might have as you are listening to this lecture. Over here we looked at a model where we said that we are looking at the difference between t, sales at time t, and t minus 1. And here suddenly I move into the difference between ln of sales at t plus 1 minus ln of sales at time t. How can I just do this? Here is how you can think about it. What we are doing with first differencing is establishing a relationship between differences. That's where the name comes from. So I will explain this through a slightly different scenario. Let's say we are talking about exchange rates and we are talking about differences across days. What this model then would tell us is the following, that the spot exchange rate today minus the exchange rate yesterday is based on this relationship which connects this difference with the difference between yesterday and day before yesterday. Once this relationship is established, then we can say the following. We want to predict the rate tomorrow. So if we want to predict the rate tomorrow, then we use that same relationship where we now have B0 and B1. So the rate tomorrow minus the rate today is based on that same relationship where this would be the rate today minus rate yesterday. The rate today is known, the rate yesterday is known, the coefficients are known. So we know the predicted value of the difference between tomorrow and today. We know the value today, and then we add the difference to get the predicted value for tomorrow. Hopefully that made sense. Moving average time series models. Moving averages are important in general because they are used often in finance, especially when we look at stock market data. But the learning objectives do not mention moving averages, and I don't see questions at the back with moving averages either. So I won't go into the details or the examples from this section, but you still need to know these two facts. The first fact I've already alluded to, which is that some time series data such as stock market returns, here moving average based models are better than AR models. an n period moving average of the current and past n minus 1 values of a time series, and this is the time series, is calculated as follows. All this is saying is what is a moving average. So if you are taking the moving average of the S&P 500 and you are taking a 30-day moving average, then what will you do? You will take the current value of the S&P 500 and then the previous 29. So in other words, you will have a total of 30 values for the S&P 500 and then you will divide by 30. That will be the 30-day moving average. What that does is, if your S&P is moving like this, then it sort of takes the average of all the numbers. So it helps you smooth the data. It helps you get rid of the daily fluctuations. Alright, section 7, and this is quite testable. This is mentioned in the learning objectives. Seasonality in time series models. Seasonality is common in time series data. If the error term of a time series model shows significant serial correlation at seasonal lags, the time series has significant seasonality, and we look at examples. This seasonality can often be modeled by including a seasonal lag in the model, such as adding a term lagged 4 quarters to an AR model on quarterly observations. All we are saying is that if you look at quarterly sales data, for example, there probably is a relationship between sales in a given quarter and sales in the same quarter last year. And using a AR1 model might not be appropriate, because then you are not using the information from 4 quarters ago. If you look at information over here which has to do with retail sales data in the US, notice that there are spikes, and they are all spikes at the same point in time. And that is probably because in the US, the sales or retail sales generally peak in the November-December timeframe. Right? So if you are modeling sales and you are only looking at AR1 data, then you are missing the fact that there is clear seasonality. And that is what we will talk about here. There are 2 examples in the curriculum, 15 and 16. We'll do one in this lecture and the other one you need to look at on your own. We will look at example 15. Example 16 is quite similar. That will get into 12 lags. But here we will look at quarterly data, so we will look at 4 lags. So I want you to pause the video and just read this example. I will then explain what needs to be done. This is a difficult problem because we are connecting lots of concepts. We are looking at sales data, which generally grows exponentially. So we will have the natural log. Our data is not covariance stationary, so we will also have first differencing. And our data is seasonal, so we need to worry about that too. And this is a regression. So this is almost as hard as it gets. It is covering almost everything that we've learned. Okay, so this is the company we are evaluating. The first thing that we do is set up an AR1 model. So what is an AR1 model? Where we are looking at the sales from period T. So we are looking at the natural log of that minus the natural log of sales from T minus 1. This is along the lines of what we saw before. Why are we doing first differencing? Because we have probably a unit root issue. The data is not covariance stationary. But we are saying this is an AR1 model, which means that this is being regressed against one version or one period earlier, which would be what? St minus 1, or the natural log of that, minus the natural log of S T minus 2. So that is shown right here. Okay, so we do this regression, and what do we get? We get an intercept term, a lag term. Does this look, do these t-stats make the regression look significant? Yes. Yeah, it makes the coefficients look significant. But can we happily move on, or do we also need to look at the autocorrelation of the residual terms? We need to look at the autocorrelation of the residual terms. I hope you remember where the standard error comes from. This is 1 over square root of t. When we do a lag 1, we get this number, and the t stat is not significant. Is this good or bad? This is actually good. But look at this number, 0.4, and here is the one that should immediately give you the red flag alert. Why? Because this is bigger than 2. But does it surprise you? You are looking at sales data. In fact, you are looking at quarterly sales data. And what this is saying is that there is substantial information in 4 lags. In other words, that there is information in the residuals that is not being captured in the model. Now, you might not be an expert at regression, but hopefully this tells you that you need to re-specify your model, and you need to include that term from 4 periods ago. But it's not as simple as just adding that 4 period ago term. You still need to worry about first differencing. How do we do that? If you look at this expression now, so we still have ln of sales at time t minus ln of sales at t minus 1 is equal to b0 plus b1, and then what is this? This is the 1 lag earlier, so b1 into ln of s t minus 1 minus ln of s t minus 2, and then we want to include the 4 period ago data. So what would that be? Plus b2 into ln of sales from t minus 4 minus ln of sales from t minus 5. This is capturing data from 4 periods ago. More specifically, it is capturing the difference of sales from t minus 4 to t minus 5. Alright, so I hope you get the idea. You run this regression and then you get your coefficients. Now you have a lag 1 coefficient and a lag 4 coefficient, and you have your t stats. Do the t stats look good? So this looks good. What about these t stats? These also look good because here nothing is above 2. So the absolute value is less than 2 for all these numbers. Okay, so that means that our model now appears to be better specified. We don't have an autocorrelation issue. But if you get something like this, you will still need to plug in here. I will not do this as part of the lecture because it is fairly mechanical, plus the working is in your book. You will be given these various sales numbers, and using the same sort of logic that we just used, you will have to predict sales for the next period. And I hope you recognize that now your prediction is based on sales in the previous quarter as well as sales 4 quarters ago. Or more specifically, it is based on the difference between this period and previous period, and the difference between 4 periods ago and 5 periods ago. Now, in case you feel that there isn't enough complexity in your life already, we are going to talk about autoregressive moving average models. Fortunately, this is not mentioned in the learning objectives, right? But it will not take a genius to figure out that the acronym for this is ARMA, autoregressive moving average. And what does this do? It combines autoregression and moving averages. Again, I don't think you'll be tested on this because it is not in the learning objectives and not mentioned in the practice problems, but the curriculum itself says that ARMA models have several limitations. I want you to read the limitations shown here. This has been taken from the summary. Next, this is in the learning objectives, so you need to know this, and it is not as bad as it sounds, but let us just look at what it sounds like. Autoregressive conditional heteroscedasticity models. This sounds like a mouthful, but if you think for a moment, you know all these terms. What does autoregressive mean? Autoregressive means that when you regress the error terms with each other, there is a problem, that there is some relationship. So that's what autoregressive means. What does conditional heteroscedasticity mean? The conditional heteroscedasticity means that the variance is changing with x. Right? So autoregressive conditional heteroscedasticity just combines those elements. And let's read the formal definition. The variance of the error in a time series model sometimes depends on the variance of previous errors. Right. Notice that we are talking about errors, we are talking about depending on each other, and we are talking about variance. So all those combined lead to something called autoregressive conditional heteroscedasticity. So if you break this complicated term into the components, it makes sense. Analysts can test for first order arch in a time series model by regressing the squared residuals on the squared residual from the previous period. Okay, so now we are regressing the squared residuals because the squared residuals are an indication of the variance. Remember, earlier we were just regressing the error terms or the residuals. Now we are regressing the squared residuals because we are concerned about whether the variance will change or not. So this still involves a regression of the error terms. When you do this, you essentially will get a regression equation which looks something like this. The error term squared at time t is equal to a naught plus a1 into error term at t minus 1 squared plus, since we are already dealing with error terms, then we have this u for the term which has an expected value of 0. When we do this regression, what are the coefficients? Normally the coefficients are called b, but now we are calling the coefficients a in this context. So we run this regression. How will we know whether we have arch or not? If a1 is 0, so you run this regression, which is regressing the squared error terms with the previous version of the squared error terms. Do you want to have a relationship between the square of the error terms and previous ones? You really don't want that relationship. So if you don't want that relationship, then what do you want a1 to be? You want a1 to be 0. So you set up a null hypothesis with a1 equal to 0, and hopefully you will not reject the null hypothesis. So then the data implies that you should not reject the null hypothesis. Then that would mean that would imply that you probably don't have an arch issue. But if you reject the null hypothesis that a1 is 0, then the model is said to have arch, or you can say it is a arch model. And you can probably understand why people generally refer to the acronym rather than the full name. Okay, so we'll just call this the arch model, but you need to know what that is. Let's say that you do this and you realize that a1 is significant or it is different from 0. Then what do? Then you want to be able to predict the variance. And how do you do that? You do that using this. So the predicted variance in the next period is equal to a naught. Where did a naught come from? From this regression. Plus a1, which also came from that same regression, times the error in period t. So even though you don't like the fact that the variance is changing, but at least you can predict that variance using this. If the examiners are not in a very good mood, they will test you on this because they are allowed to. It's explicitly mentioned. I have not said this here in the normal slides, but there is roughly a 1.5 page example, example 17, where they talk about this. But the concept is exactly what I have just discussed. All right, we are coming close to the end of this reading. Regressions with more than one time series. Do you think these are common? Where you deal with more than one time series at a time? They are actually very common. If you think about it, how do you come up with the beta of a stock? What do you regress? You regress one time series, which is the returns on the stock, versus another time series, which is the returns on an index. So running regressions where you are dealing with two parallel time series is quite common. What are the sorts of issues you might see here? You need to actually do tests to determine whether either time series has a unit root problem. You are dealing with two time series, so figure out whether either one or both of those time series have a unit root problem. What are the different scenarios that might show up when you are evaluating two different time series? One is that neither of the time series has a unit root. Is that good news? So this is good news. You can then run your linear regression because we don't have a unit root issue. If one of the two time series has a unit root problem, in other words, it is not covariance stationary, then do you have a problem? Yes, this is a problem. Then you cannot run the regression. You need to do something else. All right. What if both your time series data have a unit root problem? In other words, both your data sets are not covariance stationary. Then you need to test whether the data is co-integrated. What that means is, are both data sets impacted by the same factors? Are both data sets following the same trends? If they are, then you can run a regression. In other words, there is a unit root. Both data elements are not covariance stationary, but they have the same issues in the sense that the same factors impact both the time series and the trends are the same. Like both go up and down generally together, not exactly the same, but they trend up and down together. Then you can use regression. On the other hand, if they are not co-integrated, then you cannot use regression. All right. Again, this is a tough one. I think most probably if you get a question on the exam, you can solve it based on what you just heard. If you have time, then read through these examples. They are not very long, but they illustrate what I have just said. Section 11. This is not mentioned in the learning objectives, but all I've done is reproduced one of the paragraphs from this very short section. This paragraph is saying that even though you might think you've learned a lot, but there is a lot more to this, right? And one of the things that you haven't talked about, for example, is the uncertainty of the forecasts. We've talked about forecasts, but we haven't talked about measuring the uncertainty of those forecasts. What this is doing is simply making you aware that there is a lot that you still don't know. But wise people have a sense for what they know, as well as they have a sense for what they don't know. All right, so I don't see how you can be tested on this as long as you remain humble and say, okay, I've learned a lot, but there is a lot more out there. All right, section 12, suggested steps in time series forecasting. This is an excellent summary of a lot of what we've studied in quant. I'll make a bit of a disclaimer here. Normally what I do is I look through the curriculum and I pick out what I think is most relevant, most testable, and then I make you do examples, and then I also have you do some examples on your own, and then I say you do the questions at the back. As I read through this section, I thought it was so good that I could not figure out what to pull out. So then what I did is I just reproduced that section from the curriculum over here. In fact, normally the curriculum, or often, especially in quant, the curriculum presents things in a somewhat difficult manner. But here things are presented nicely in bullet points, and it's very easy to read. In fact, this is a step-by-step guide to building a time series model. And I actually want you to read through this on your own. So the basic idea is to help you figure out which model to use. You first try the simple trend model, and then if that works, great. If you see there is an exponential element to your data, then you transform. You check whether there are any error correlation issues. If they are, then you move to a more sophisticated model such as AR. And then with AR models, you need to check whether there is seasonality or not. You need to check whether the data is covariance stationary or not. So over these slides, it's just a step-by-step description of what to do. And I'm pretty confident that if you've understood everything that we've said so far, then you can read through this without much of a problem. All right, there are 9 things to do, so read these. That is it. Read the summary, and I would really say there are 2 aspects to the summary. One is the few slides I just ran through. Actually, I hope you paused and read through them. The other is the actual summary in the curriculum. Do that. Review the learning objectives and make sure you can say something sensible about every learning objective. I have gone through several examples. The ones that I haven't covered, you should do. In fact, even the examples that I have covered, you should read them, and you will find that it's much easier to do them once you've heard the lecture. Do the practice problems. Practice problems includes questions which are not in the standard case study MCQ format. But I would still encourage you to at least read the question and try to think about a solution and then look at the solution. If you have more time, then come up with your solution. Even though it's not MCQ type, but those concepts can show up on the exam. And also try to practice questions from other sources. That is